Hi, and welcome back to Understanding Motors. Last episode, we discussed how, using Hall effect sensors, we're able to detect which of 6 rotational sectors a brushless motor's rotor is in. We also talked about how, in order to maximize torque in a brushless motor, we want to induce a magnetic field which is perpendicular to and leading the rotor's magnetic field. In brushless motors, we relied on physical movement to handle the commutation of the motor and keep the current path optimized for maximizing our torque. Without brushes, this is no longer an option, and we have to handle commutation entirely electronically. And this brings us back to our old friend from episode 3, the H-bridge. If you remember from earlier, the H-bridge is an electric circuit that connects a load to both a positive voltage and ground via several MOSFETs, which we model as the combination of a switch and a diode. This works great for our brush motors, which only have 2 wires coming out of them. But our brushless motors have 3 wires. To handle this, we add a third pair of MOSFETs which bridge between high and ground. We call this a half bridge since it represents half of an H-bridge. Thus, to drive a brushless motor, we use a circuit with 3 half bridges, where closing this switch will connect phase A of our motor to high, this switch will connect phase A to ground, this will connect phase B to high, this phase B to ground, this phase C to high, and finally this phase C to ground. In addition to the brushless motor improvements we've already discussed, ditching the physical brushes comes with a couple of additional, more nuanced positive side effects. Firstly, since all 3 motor phases are constantly electrically connected to power and ground through diodes, whenever we stop commanding current to a phase, it will decay to 0 smoothly in the first order manner discussed in episode 3. In the case of a brushed motor, when a brush physically lost contact, current could be forced to arc through the air to the brush. Additionally, and much more importantly, by abandoning the brushes in favor of the 3 half-bridge system, we gain the ability to control all 3 phases independently. Thus, we can arbitrarily and individually connect each of the 3 phases to power, to ground, or leave their voltage floating, regardless of the rotor's orientation. This means that at any time, we could connect 1 to power, 2 to ground, 2 to power, 1 to ground, all of them to power, all of them to ground, and so on. While the usefulness of this ability may not be immediately obvious, it will prove to be incredibly important in episodes 9 and 10 when we move on to more intricate commutation methods. But for now, we're just going to start simple with what's called 6-sector block commutation. Here, just like with brushed commutation, only one of the motor's nodes is connected to ground and one is connected to high at a time. In fact, what we essentially want to do with block commutation is replicate exactly what we were doing with brushed commutation, just without the brushes. Recall from episode 2 that for the 3 motor phases, each spaced 120 degrees apart, the torque curve looked like this. As we talked about last episode, the underlying physics are still the same, so this will be true for our brushless motor. However, since we now care about the reaction torque on the magnet, not the torque on the windings, our curves will be flipped. Looking at these curves in episode 2, we found that as our rotor moved, we only needed to connect our nodes to high or ground when they were within 60 degrees of parallel to our magnetic field. The same analysis will hold true for our brushless motors when using block commutation. The only differences are that, because the sign of our torque curves flipped, we will reverse which side is connected to high and which side is connected to ground, and that before, our magnetic field was static and our winding diagram was rotating. And now our winding diagram will be static and our magnetic field will rotate. Since our magnetic field was static in our brush configuration, the ranges where we needed to connect to high and ground were also static, and we were able to design brushes that took care of our commutation for us. Now, however, this isn't practical. Instead, we will place the Hall effect sensors that we talked about last episode strategically around our rotor, so that the boundaries of our 6 Hall sectors mark the locations where our H-bridge needs to change configuration. Progressing through the 6 Hall sectors, we can thus develop a table of what node we want to connect to high and what node we want to connect to ground for any given orientation. When in Hall sector 0, we see that node C needs to connect to our high voltage and node B needs to connect to our ground, so we can set our H-bridge accordingly. As we progress our rotation and enter Hall Sector 1, Node C is disconnected from high and Node A is connected there instead. Continuing to rotate, as we enter Sector 2, we now want to disconnect B from ground and connect C to ground. In Sector 3, we will disconnect A from high and swap B in its place. For Sector 4, we will disconnect C from ground and connect A there instead. Finally, in Sector 5, we will disconnect B from high and swap C in its place. We will then go back to Sector 0 and repeat this pattern as long as we want to rotate. On a side note, the table for rotating the motor clockwise instead of counterclockwise would be the same, except what we had previously connected to high for a given sector would now connect to ground, and what we had connected to ground would now connect to high. So now we know how to handle basic commutation in our brushless motor. However, in addition to dictating the path our current takes through our motor, the H-bridge also allows us, once again, to modulate the amount of current running through the phases by modifying the PWM signal we send to the MOSFETs. And different methods of modulating the current can have drastic effects on the efficiency of your system as well as its electrical dynamics. And this is what we're going to begin to explore next episode.